Welcome back to chapter one. This chapter is going to be a lot of functions and just stuff about functions. It should be mostly review. We may hit some new vocab words. We may hit some little tweaks of things that you may not have seen before. But again, for the most part, this chapter should be mostly review. Um, this first section, we're going to be looking at modeling and equation solving. Some of this is stuff that you should know. Some of it is stuff that you might know, but maybe you've never really thought about before. So we're going to take a look at this. First of all, our learning targets. We're going to model data numerically, algebraically, and graphically. We're going to solve applications involving models and equation solving. We're going to solve equations algebraically and graphically. And we're going to answer conceptual questions involving modeling and equation solving. So first of all, we have some mathematical models. We have three main types of mathematical models, and they all have their uses. The first type we're going to look at is called a numerical model. Now, a numerical model is basically just a table of values. It's data. It's something like this. Like, does this tell us all that much in and of itself? Not particularly. It's hard to visualize what this says, but we can find stuff out about it. If we were looking at this, we could figure out in what year the number of passengers increased the most. We would just have to figure out which difference between years was the biggest. Um, and so we can figure stuff out with this, but it is fairly limited in what we can do. A lot of times, though, this is where we start with any kind of mathematical modeling. Another type of model is an algebraic model. An algebraic model is an equation. We could have maybe the model we're looking at the best deal for pizza. We have a bunch of pizzas that they're round because we're at a place that gets round pizzas, and so they all have different prices depending on how big they are. Well, we want to know how much pizza you get per dollar, so we could figure out how much pizza divided by the cost. To figure out how much pizza, we'd be looking at the area, and so being that it's round, where's my equal sign? There we go. Area equals pi r squared. And so we could take the radius of the different pizzas, find the areas, and then be dividing by the price to figure out how much pizza we get per dollar. Um, and so that would be an algebraic model that we could use to solve things. Pretty much any equation that we ever work with is an algebraic model to something. It just might not be all that exciting. The other type of model is a graphical model, and this is a graph. So it could be a like a line or a parabola or something like that where it matches the algebraic model, it matches the formula precisely. It could be something that comes from data that's not particularly pretty. Like this isn't a line. Like we're not going to get an equation that's going to match this data perfectly. That's okay. It's a model. It's not necessarily a perfect thing. Later on, we will find ways of getting the line of best fit, which could be right around in there, which would become an algebraic model for this graph. Going from a numerical model to a graphical model is one of the things that we do pretty regularly because it's just graphing points. So it's easy, it gives us a visual of what it is that we're looking at, and it allows us to see things, it allows us to see the shape. This one looks like it's fairly linear. I mean, there's some variation there, but we could make an argument that it could be linear. It doesn't look quadratic, so it allows us to see that. But by looking at the data, it would be a lot harder to see that. And that's with like actual data. Actual data is not pretty. Now, a lot of what you're going to be doing, like you will be doing some actual data type stuff today, but you'll also be working with tables based off equations where it's not actual data, where it does actually work out to be pretty. Something like this. Here we have x and y. X goes 3, 5, 7, 9, 12, 15. And then y goes 6, 10, 14, 18, 24, and 30. And so what you want to do is, it's important that we can see the difference in the x's. And so 3 to 5 is 2, 5 to 7 is 2, 7 to 9 is 2, 9 to 12 all of a sudden is 3, and same with 12 to 15 is 3. That little difference there makes it so that it's not quite as easy as it was back in Algebra 2 necessarily. So we find the difference in the x's, now we can find the difference in the y's. Now the y's, from 6 to 10, well, that's 4. From 10 to 14 is also 4. From 14 to 18 is 4. Hey, it's going up by 4. The x's are going up by 2. Now from 18 to 24 is 6. And from 24 to 30 is 6. That changed, but so did these upper numbers as well. Being that these are the same when these are the same, that tells us this is probably linear. You can find the slope. The slope is the change of y over the change of x. It's going to be this bottom number divided by the top number. So it's either going to be 4 over 2 or it's going to be 6 over 3. Either way, that's going to get us to be 2. So the slope is 2, and it's a line. And that was the first difference. So we're looking for the first difference. Another thing you could do, if in doubt, is you can graph the points. What shape is that? Like if you graph these, it will look like a line. These last 2 points will just be a little bit further apart than the other ones. All right, what if we have a different one? So this one, the x's are going up by the same amount each time. They're all going up by 1. And then the y's, we have from 2 to 3 is 1. From 3 to 6 is 3. From 6 to 11 is 5. From 11 to 18 is 7. And from 18 to 27 is 9. Do those go up by the same amount each time? I know some people probably say yes. Oh yeah, they're going up by 2. No, it went up 1, 3, 5, 7, 9. Now, that means it's not linear, but you notice that, hey, these are all going up by 2. So the first difference, not being the same, says it's not linear. The second difference, being the same, says it's a quadratic. So this is going to be a y equals x squared with something. For that, I'd look, let's see, 0 squared is 0, plus 2 is 2, 1 squared is 1, plus 2 is 3, 4 squared is 2, plus 2, so it's just x squared plus 2. But we know it's x squared, so start by squaring those x's and then see what you have to do to get to those y values. So we have the first difference, we have the second difference. If it was the third difference that was the same, that means it would be x cubed. If it was the fourth difference, it means it would be x to the fourth. Sometimes, so this one, we're going up by 4, 4, 2, 4, and then 6. So sometimes it just tries to trick you. This one might be easier to graph, except that those y values are pretty big. So that's going to be tough. But we can look at the x values. We'd want to be looking at the ones where it goes up by 4. See if those are always the same. Maybe the one that goes up by 2 is going to be half of that. The one that goes up by 6 is going to be 1.5 of it. So from 20 to 72, it's going to go up 52. From 72 to 156, it's going to go up something 4, 84. From 156 to 210, that's going to be 54. From 210 to 342, that's going to be 132. And from 342 to 600 is going to be 258. So where do we go from here? Well, this is a bit trickier of one because those x values aren't all going up by the same amount. But from here, what we could do, since we don't have other data, again, is we'd want to graph it. Are you going to graph it with, like, by hand and get accuracy to that? Like, maybe. If you do, I would use graph paper. Or you can graph it using a graphing calculator. You put it into list 1, list 2, you make a scatter plot, and you can get your points. So that's another way we can do it. It's not always going to go straight from numerical to algebraic. It might go through graphical. And then this one's a little different because down here, the y values are all going up by the same amount. And then the x values, we're going up by 3, 5, 7, 9, and 11. And so the x values have that second difference, which means instead of y equals x squared, it would be something more like x equals y squared, or y equals the square root of x. So if we really wanted to find it, I would start with this. I'd square all the y's, then figure out how you get from that down to the x. So like 1 squared is 1, plus 3 is 4. 2 squared is 4, plus 3 is 7. 3 squared is 9, plus 3 is 12. So we'd end up with x equals y squared plus 3. And then to get solved for y, we'd subtract 3. So x minus 3 equals y squared, square root, y equals the square root of x minus 3. So that's how you can deal with those. It's this type where things are going up by different amounts in both the x's and the y's that a graph may be necessary. Solving equations. We have a few different ways of solving equations. The best way of solving an equation, the way that gets you an exact answer, is algebraically. That's the best way. It's not always a possible way, but it is the best way. So if we have an equation like this, what we want to do is we want to get it equal to 0. So we're going to subtract the 4x to get x squared minus 4x minus 5 equals 0. And now we can factor it. And that'll be x minus 5, x plus 1, because x times x equals x squared. And then we have x times 1 and x times negative 5. So 1x minus 5x is negative 4x. And negative 5 times 1 is negative 5. So we have that. Now we have this zero factor principle, which all that says is if you have something times something equals 0, one of those things has to equal 0. So either x minus 5 equals 0, or x plus 1 equals 0. So x will equal 5 or negative 1. So we can solve that by factoring. But that's not the only way we could do it. We could solve it numerically. If we wanted to solve it numerically, we would just have to make a table. Now, making a table can be very, very time consuming. However, we have technology that can make tables for us. And so that can help. And we're looking for when does it equal 0. So to plug it into the calculator, you do need to set it equal to 0 first. And so we see it equals 0 here at negative 1 and down here at 5. So once again, x would equal 5 or negative 1. We can solve it graphically as well. Again, you could graph it by hand, but if it's going to be something complicated enough that you're going to solve it graphically, chances are your graph by hand is not going to be quite accurate enough for it to be a really good solution. And so you can graph it in your calculator. We're looking for where it equals 0, those x-intercepts. The solution, like this x equals 5, x equals -1, that's called a solution. It's called the roots, it's called the x-intercepts, and it's called the zeros. They all mean the same thing. Sometimes we use one over the other just because of in the context it makes a little bit more sense, but for all intents and purposes, they're the same thing. Now the problem with solving it graphically is that it looks like it goes through -1 and 5, but does it? Does it maybe go through -0.99999 and 5.00001? We're not going to be able to tell by looking at the graph. That's what makes that a little bit tough. Now, there are some equations that you'd get where you just don't have the capability of solving them yet. There are some that are just like, they're so crazy that like a graph is basically the only way you're going to do it. And then you can use the intercept feature or the zero feature of the calculator that gives you a really close estimate of what it's going to be. And sometimes graphing it doesn't really work, and neither does numerical. You just have to do it, like if you want the exact answer, you have to do it by hand. So something like this. We're not going to be able to factor this because what times what equals 2, that'll add to give us -4. There's nothing there. So if we can't factor it, we always have the quadratic formula. Remember the quadratic formula, x equals -b, that's that -4, so we have 4 plus or minus the square root of b squared. So that's 4 squared minus 4 times a times c. I guess that's a -4 squared. It's going to become positive, doesn't matter. All over 2a. And then we can simplify this. So 4 plus or minus the square root of 16 minus 8 over 2. 16 minus 8 is 8. And so square root of 8, 8 is 4 times 2. So this could be 2 root 2 over 2, which we can reduce. So 4 over 2 is 2, plus or minus 2 over 2 is 1, so we have root 2. So we have 2 plus or minus root 2, which comes out to be 2 answers. Root 2 is about 1.4. It's an irrational number, so we're not going to get an exact answer if we make it a decimal, but about 1.4, so this should be about 0.6 and 3.4-ish. Now if we tried to do it numerically, we're going to see that right here, it crosses from positive to negative. That means there's a root somewhere in between 0 and 1, but we don't know where. And then again, it changes from negative to positive, so there's a root between 3 and 4, but we don't know where. The numerical solution doesn't help us here. Now we could kind of zoom in on the table, like make it so that the x values go up by smaller increments, but we will still never see 0 in the y column. And so we're never going to find that exact answer using the table. And then with the graph, it crosses two places that it's impossible to see. Now here we could, if we were not able to solve this algebraically, or we were told to solve it graphically, we could use the zero feature of the graphing calculator and get a decimal approximation, but it's again not going to give us the 2 plus or minus root 2. It'll give us something that's really close, but not necessarily perfect. Again, sometimes you just can't solve it algebraically, and sometimes really close is actually good enough. If we were cutting a board to length and we needed it to be 2 plus root 2 feet, like how accurate is that cut really going to be? Like 1 or 2 decimal places is all you would really need for that. So there are times when you don't need to be super accurate, but in math, most of the time we do like those exact answers. Problem solving. So our book has a great little chunk on problem solving in this section, and so I cut and pasted some of what they have because they have some problem solving steps, and these are great. So we have George Polio's 4 problem solving steps. So he sees a problem, and first you need to understand it. What is the problem asking you to find? What is the problem telling you? All that kind of stuff. And then devise a plan. What are you going to do? Are you going to make an equation for an algebraic one? Are you going to make a graph? Like, how are you going to figure out the answer to what the problem's asking? And then carry out the plan. Well, you devise a plan, then you have to carry out the plan. You actually have to do it. And then look back. Does it make sense? And actually answer the question. Like, so often people get through it and they'll get like, t equals 7. That's great. T equals 7. That is not necessarily the answer to the problem. The answer to the problem might be the ball hit its maximum height at t equals 7 seconds. So when you have a problem, which is generally like it's considered a word problem because there's actually words involved, there's context, there's something that you're actually figuring out. It's not a naked problem, which is just like, here's the equation, solve it, like we just did on the last one. But when you have an actual problem, in your answer, you should be able to tell what the problem was asking you. T equals 7 says nothing about what that problem said. The ball reaches its maximum height at 7 seconds tells you what you need to know about the problem. There's a ball, it was going up and then it came down, it hit its maximum height at 7 seconds. We have units, we have what it was that we were answering. That is important when it comes to problem solving. We do have a couple other problem solving steps that are really similar. I threw them in here anyway, but we have the game one, where you identify the problem, you make your assumptions and identify variables. That's part of devise a plan in Polio's one. You carry out the mathematics, you actually do it. Analyze and assess the solution. Does it make sense? What does that number mean? And then iterate. In actual practice, it would be implementing the model. It would be actually doing it, making sure you have the answer as an actual answer to the problem. There's statistics ones too. You formulate a question, you collect your data, you analyze the data, and then you interpret the results. And so when I'm teaching statistics, we do a lot of this, and that's a specific problem-solving method for that. We'll do that a little bit off and on, but when we hit like a statistics unit, we don't do all that much of that right here. But we also have the steps broken down just a little bit more. So step 1, you understand the problem. Like, read it maybe a few times. Be sure you understand what it says. Restate the problem in your own words. Like, you don't necessarily have to do it on paper. You can, depending on the size of the problem, you can. Like, most of the problems we get for an assignment, like, they might take you a couple minutes max. Like, those are barely problems. Like, mathematical problems, I remember when I was in college, like, we'd have a problem, we had a week or two to do it, and we'd work on it like all week off and on, just time to think. Those are a little bit bigger, but even still, those are small problems. So you might not need to do every one of these things for the problems you're working on, but it is good to think about. Restate the problem, discuss the problem with others if you can. You may not need to discuss the problem with others, depending on, again, the difficulty of the problem. Identify clearly the information you need to solve the problem, and then find the information. Develop your mathematical model. So draw a picture, draw a picture, draw a picture, draw a picture. Pictures are huge in so many cases. The picture might be a graph. The picture might be a diagram. Like, if you're dealing with a triangle, like, the picture is going to be a triangle where you can label it. You can see the relationship between the different values. But draw a picture. That is such an important step in problem solving. Introduce a variable to represent what you need. Hey, we have something that's unknown. What do? We give it a name. The name might be X, it might be H, it might be Fred. I don't know. It's your problem. And then use a statement of the problem to find an equation or an equality. So that would be setting up that algebraic model if it's going to be an algebraic type model. Chances are, yeah, you're probably going to want some sort of an algebraic model. It might be a formula. It might be a line of best fit where it doesn't fit the data perfectly, but it still does a decent job at describing it. And then you're going to solve it algebraically, graphically, numerically. I would, if you do it, regardless of how you do it, I would use another method to double check. If you solve it algebraically, great, graph it. Does your algebraic answer make sense with the graph? If you do it graphically and you can't do it algebraically, see if you can do it numerically. Does that make sense? And then interpret the solution in the problem setting. That would be take it back from your answer, which is like t equals 7, back to the sentence where you can see exactly what the problem was asking by looking at your answer. And then obviously you need to decide if it makes sense. You throw a ball in the air and it hits its maximum height at -4 seconds. That doesn't make sense. Like, it should hit it at a positive value. So that means that something happened there. And finally, for this section, we have some cautions when we've talked about using the calculators to graph things. Well, we have some grapher fails. And grapher, because it might not be your calculator, maybe you're using Desmos or another graphing utility. So grapher is just that generic graphing utility term, and it's also kind of fun to say. You have your grapher. So we do have some things where it just doesn't really work. This one would be a grapher fail. We look at this graph and it just kind of ends here and here. Does it have x-intercepts? It doesn't look like it. We don't see any x-intercepts there. It just turns into errors. Well, what it has is it has asymptotes. And so the problem with the grapher here is it's plugging in numbers. It's plugging in 1.4, 1.3, 1.2, 1.1, and getting those values and connecting the dots. And then it gets to 1, and that's an error because the denominator, that would make it equal to 0. And so that's generally frowned upon. However, and it's doing it in smaller increments than just 0.1, but it still hits a place where it has that jump where it goes from a value to an error and then it just shuts down. It doesn't know how to deal with that. If we wanted to find the 0, so we have 0 equals 3 minus 1 over the square root of x squared minus 1. We could add that over. 1 over the square root of x squared minus 1 equals 3. We can multiply by this guy to get 3 times that equals 1, but let's divide by 3 as well. To get 1/3 equals the square root of x squared minus 1. We can square both sides. 1/9 equals x squared minus 1. Add 1, that which would be 9/9, so we'd have 10/9 equals x squared, and then square root. So x would equal plus or minus the square root of 10 over 3. And so, which is just above 1 or below -1. And so that's when it's going to hit 0. And if we actually were able to graph this, it would come down and it would have a vertical asymptote there. But with the way that the graphing calculator is programmed, we just can't see that. And so that doesn't mean it's bad. It just means we have to be aware of that possibility and not just blindly trust the graphing calculator. Another failure that the graphing calculator can give us, and this is more of an operator error. That first one is a programming thing. This one's an operating error. So if we're looking at this, we see we have a 0 here, and that's kind of it. Oh, there's something going on over here as well. But that doesn't really show us much about the function. Know what it is that you're graphing. You need to know some information about it. Notice, so here, the x's are going from -10 to 10, and the y's are going from -10 to 10. If we just zoomed out generally, like the -10 to 10 is actually okay. We're seeing what we need to see there, but it's the y values that are the problem. So if we change our window, so we're going from -10 to 10 and -500 to 500, we see the function looking like this. And that allows us to see what it actually looks like. It looks like it's this cubic. It has that 0 here, it has that 0 here, but it gives us more of a clear picture of what it is that we're looking at. If we just graph it using the normal settings, and we get that doesn't tell us much. If you copied that onto your paper, that's not the graph of the function. You should actually see the function in your graph, in your viewing window, which could be on your calculator, your viewing window could be on your paper, but you should actually see the graph. It should not go off like that. And so make sure that you have some awareness of what your function looks like and what your values are when you're using your graphing calculator, so that you don't do something horrible like give me a graph that looks like that, because nobody wants to see that. And so this is section 1. We'll continue our look at functions and stuff like that in the next section, and I'll see you in class. But until then, keep working problems, keep asking questions, and as always, happy mathing.